How text becomes numbers for AI models. By the end, you will know how raw text turns into tokens and integer IDs. You will see a simple Python pipeline that normalizes text, builds a stable vocabulary, counts frequency, prunes rare words, and reconstructs readable text. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Representing text as numbers matters because models operate on integers and vectors. The core property it optimizes is consistent mapping. Consistency keeps training and inference aligned. The main trade-off is size versus fidelity. Keep every word and memory grows. Prune aggressively and you get more unknowns and potential errors. At a practical scale, even 1,000 short sentences shows how pruning changes the unknown rate and index compactness. The intuition is simple. First, you break a sentence into small pieces. Then you give each piece a stable number. You can count how often each piece appears and decide which ones to keep. This shines when you need deterministic IDs for downstream models. It limits nuance for rare or misspelled tokens, which is the main limitation. We will build a tiny, self-contained demo that shows all steps and a readable round trip from sentence to IDs and back. Now we split a sentence into words and normalize case. This snippet lowercases a sentence and extracts word tokens with a regex. It creates a small example text in the variable text, so the demo is self-contained. The function refindAll, which finds all word-like chunks using a pattern that matches letters and digits, pulls out each piece. Calling lower on the text keeps token matching consistent, so cats and cats become the same token. The variable tokens is a plain Python list that holds the sequence the model would see conceptually. The printed list shows the normalized tokens in order, which is the starting point for IDs. Next, we make a deterministic mapping from token to integer. This snippet builds a vocab and maps tokens to integer RDs deterministically. It reuses the tokens idea and then makes vocab by sorting the unique tokens and assigning each one an index. The sorted function gives a stable order, and enumerate, which pairs each item with a consecutive index, produces compact consecutive numbers. The dictionary vocab stores token to ID mapping, and the list IDs applies that mapping to the token sequence. Sorting ensures the same token always receives the same ID across runs. The printed list is the token sequence expressed as integer IDs, which models actually use. Now we check which tokens matter most by counting. This snippet counts token frequency and prints the top 3 tokens. The variable CNT is a counter, which tallies how often each token appears in tokens and gives a simple frequency table. We then sort token count pairs by count in descending order and by token alphabetically to break ties deterministically. The sorted function with a custom key makes that stable ranking possible. Taking the first 3 items shows the most common pieces of text, a basic signal of importance for pruning or weighting. The printed list shows those top tokens and counts, which is useful when you want to prioritize vocabulary members. Next, we prune rare words and reserve an unknown token. This snippet drops rare tokens and maps the rest to IDs with an unknown placeholder. We keep tokens that appear at least min frequency times, sort them, and assign IDs starting at 1, so we reserve the value 0 to represent anything not in vocab. The vocab get method with a default value returns 0 for unknown tokens, mirroring how production tokenizers handle out-of-vocabulary items. Increasing min-freq prunes more words, which raises the number of zeros and shrinks memory usage. Decreasing it keeps more words, but grows the index. The printed IDs show known words as small integers and unknowns as 0, clarifying that trade-off. Finally, we show a round trip back to readable text. This snippet converts IDs back to a normalized text string. It reuses the sorted unique tokens in SRT and the vocab that maps each token to its ID. Instead of building a reverse dictionary, the code indexes SRT by each token ID to recover the original token sequence. The join function assembles those recovered tokens into a single readable string. This simple round trip shows how integer IDs still preserve enough information to reconstruct text when the vocab is known. The printed sentence confirms the mapping is consistent and reversible, as long as you kept the same vocabulary. Recap: it is a pipeline that normalizes text, maps tokens to stable integer IDs, and can reconstruct text when the vocab is shared. Use this when you need deterministic IDs for model training, serving, or simple corpus analysis. One caveat: aggressive pruning introduces unknown tokens and can hurt downstream accuracy for rare but important words. Next step: experiment with the pruning threshold min-freq and measure how the unknown token rate and reconstruction quality change as you vary that number. If you want to scale further, add an approximate nearest neighbor index for ID to embedding lookup, but start by tuning min-freq. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.